acid and base systems. We've done common ion before in our unit on solubility product. You can go back and watch the video there for some more refresher questions. I'm going to work through a couple of problems with you today, specifically in acid and base systems. The common ion effect is the same as it was in the solubility unit. When we add an ion in common, we'll get an equilibrium shift. It's going to shift to reduce the concentration of an added ion in common, and that will reduce the amount of dissociation. Whenever we add an ion in common to an acid-base system, it will shift the equilibrium and affect our pH. Consider this basic system. Suppose we have a system of ammonia. Ammonia is NH3, and it's a 0.25 molar solution. I've given you the Kb for ammonia, Kb because it's a base, and I want you to calculate the ammonium ion concentration. We can also calculate the pH here, and also figure out how that would change if we add sodium hydroxide to the solution. In order to figure this out, we're going to start with a balanced equation. The formula for ammonia is NH3, but when I go to try to write a dissociation for NH3, we quite often get confused. Ammonia itself does not dissociate. So how am I going to write a balanced equation? And if I'm going to need to get pH and calculations of that nature, how do I get on the square? To get on the pH square, I need to get either a hydrogen or a hydroxide. The answer is to write this as we would with all non-hydroxide type bases by adding water to the ammonia and writing it in the form of a Bronsted-Lowry reaction. When we write ammonia plus water as a Bronsted-Lowry reaction, we can see that the ammonia being a base will be a proton acceptor to form the ammonium ion, and the resulting from the water will turn into the hydroxide ion. As with all acid-base reactions, with weak acids and bases, we will write two-way arrows so that we can use our equilibrium expression. The equilibrium expression for the dissociation of ammonia would look as follows. Kb is equal to the concentration of the ammonium ion times the concentration of the hydroxide ion over the concentration of ammonia. Liquid water is not included in equilibrium calculations. We know from the question that the concentration of ammonia is 0.25 molar. The concentration of water is not relevant to this equation, and the concentrations of ammonium and hydroxide are unknown. Because from our balanced equation we see they occur in a 1-to-1 ratio, I will use the value x to stand in for their unknown concentration. Let's separate these values that we have in blue into our Kb expression, as we know the Kb for ammonia is 1.8 times 10 to the minus 5. Substituting, value of Kb is 1.8 times 10 to the minus 5. The concentration of ammonium is x, as is the concentration of hydroxide, over the concentration of ammonia, which is 0.25. Doing the math to solve for x, we come to a value of 0.002. Up above, we defined x as being both the concentration of ammonium and hydroxide. So at this point, we know the hydroxide concentration and the ammonium concentration. They will both be 0.002 molar. Let's take this one step further and solve for the pH of this solution. Being a base, we will expect the pH of this solution to be a number higher than 7. Since I don't yet have a hydrogen ion concentration, I will start by solving for the pOH. The pOH is given as the negative of the log of the concentration of hydroxide. In this case, it will be the negative of the log of 0.002. That works out to a value of 2.67. Now, pH is equal to 14 minus the pOH. 14 minus 2.67 is 11.32. As expected, we got a value that was greater than 7. But the question also asks us, what would be the concentration, and we will also solve for the pH, if we also add sodium hydroxide to this solution? Now we have a common ion problem. We still have the ammonia in water scenario, and their concentrations initially are still at 0.25 x and x. We know we're going to have a change and an effect of those change because this is a common ion question. I have two different salts that have an ion in common. In this case, both salts contain hydroxide. Whenever you have a situation with two different compounds that have an ion in common, you're going to need to do an ice chart and do some calculations. Since our sodium hydroxide concentration is 0.1 molar, and it is a strong base, it is a salt that will dissociate completely, we can use a 1 arrow and assume that all of it breaks down. Because one sodium hydroxide breaks down to give me 1 sodium and 1 hydroxide. In solution, the concentration of the sodium ion and the hydroxide ion will both be 0.1. In both salts, we are adding hydroxide. So to the initial amount X of hydroxide that we had from the ammonia in the water, we will now add 0.1 moles per liter of hydroxide that came to us from having the sodium hydroxide added to the water. We know the value for X was very small. It was 0.002. When we add that to 0.1, it is still effectively 0.1. The concentration of ammonium now will be less. This equilibrium is going to shift to the left. We still don't know the concentration of the ammonium ion, so I'm going to leave that value as X. We don't know what the concentration of ammonia is going to be, but we know it should stay close to its initial value of 0.25. Using our equation, equilibrium equation for ammonium in water, Kb is the concentration of ammonia times that of hydroxide over that of the ammonia. Our Kb was 1.8 times 10 to the minus 5. That has not changed. The value for the concentration of ammonium ion, however, is still X. The concentration of hydroxide will be 0.1, and the value of the ammonia is still 0.25. Doing the math and solving for X, we get a value of 4.5 times 10 to the minus 5. Since X is now defined as the concentration of the ammonium ion, we now have a new concentration of ammonium. If we want to solve for the pH, we will first have to solve for the pOH. Our concentration of hydroxide is now approximately 0.1. Since pOH is the negative of the concentration of hydroxide, the negative of the log of 0.1 is 1. pH then is 14 minus the pOH, and we get a value for the pH of 13. We added a strong base, and as expected, this solution became significantly more basic. Let's try a question using acids. In this case, the acid we're going to use is hypochlorous acid. Hydrogen hypochlorite is named hypochlorous acid. The Ka for this acid is given as 3 times 10 to the minus 8. Suppose I have a 0.5 molar solution of this acid. Calculate the pH. Then we're going to add a salt. We're going to add the salt lithium hypochlorite. That lithium hypochlorite will come in at 2 times 10 to the minus 4 molar concentration. And we'll find the hydronium concentration and a new pH. Now remember, hydronium is the concentration of my hydrogen ion. pH is the negative of the log of that concentration. As always, we're going to start with a balanced equation. Hypochlorous acid, like all acids, will only ever dissociate one proton. So HClO will break down to give us hydrogen and hypochlorite ion. The concentration of the hypochlorous acid was 0.5 molar. The concentration of the hydrogen ion and the hypochlorite ion are unknown, but they will be in a 1-to-1 ratio, so we refer to them both as X. Our Ka expression will be H ion concentration times hypochlorite ion concentration over the concentration of hydrogen hypochlorite. Substituting the values, we know Ka, it was given in the question. The concentrations of hydrogen and hypochlorite come both in at X, and the concentration of our hypochlorous acid is 0.5. Solving for X, we get a value of 1.22 times 10 to the minus 4. And X has been defined as the concentration of my hydrogen ion. Now, since pH is the negative of the log of that concentration, the pH of this solution will be 3.91. We know that we're going to get a value less than 7 because we're dealing with an acid. How does this all change now if I add a salt that has an ion in common? When we add lithium hypochlorite to the solution, it dissociates completely to form lithium ion and hypochlorite ion. As before, the ion in common is the hypochlorite ion. In this scenario, we're going to end up with 2 times 10 to the minus 4 moles per liter of hypochlorite ion. This is going to be added to the amount of hypochlorite ion from the hydrogen hypochlorite. This ion is added in common. Since X plus 2 times 10 to the minus 4 will be approximately 2 times 10 to the minus 4, we can assume that this will be the approximate total concentration of hypochlorite ion. This time, when we enter these into our equilibrium expression, in place of the hypochlorite ion concentration, we will enter the value 2 times 10 to the minus 4. Now solving for X, we get a value of 7.5 times 10 to the minus 5. It's a much smaller value. Taking the negative of the log of this value gives us our pH, which is now 4.1. At the back of your acids bases workbook, there is a worksheet with 6 questions on it titled Common Ion Effect. I would like you to work on this worksheet to practice solving for common ion problems.